Okay, so we are moving over to chapter 11. And chapter 11, since we're still discussing hydrocarbons, remember hydrocarbons, this is a collective term to refer to alkenes, well, starting with alkenes, and alkynes. So these are all those organic compounds that only have hydrogen and carbon in the formula. So we discussed alkanes in chapter 10. We went into details, unfolded and unpacked everything. Now we're looking at alkenes and alkynes. And so I'm going to move over and start with alkenes and alkynes. So chapter 11 has us studying both alkenes and alkynes at the same time. And so I took a bunch of slides out to kind of focus on the most important parts. With alkenes and alkynes, we're looking at two families of organic compounds that contain multiple bonds. I mentioned this yesterday. Alkenes have at least two carbons that have a multiple bond. So they have two carbons holding a double bond. So this is called the carbon-carbon double bond. Then alkynes will have a carbon-carbon triple bond. So you have to have at least one of those. Now at you guys' level, we focus on just compounds having one alkene or one alkyne. We don't look at compounds that have multiple double bonds or multiple triple bonds. We're trying to keep it simple, okay? So alkenes are compounds that contain a carbon-carbon double bond. And so saying it this way describes two carbons held together by a double bond, a carbon-carbon double bond. Okay? So when you have a carbon-carbon double bond holding the two carbons, of course, we have an alkene. And what we see here is because of the double bond, the shape of the molecule changes. Now, I gave you guys a little table that shows you how to figure out the different shapes. And of course, one of your labs asked you these questions. Real quick, to go over the shape around the carbon-carbon double bond, I will look at each carbon at a time. So the carbon on the left here is surrounded by three groups of electrons. Okay, there's a single bond here that counts as one group. The second single bond, the second group, and then these double bonds together are the third group. So for the carbon on the left, the carbon is surrounded by three groups, and all groups are bonded groups. So if you go to that chart, which I'm not going to pull up right now, but if you go to that chart and you read the chart, it actually shows you what shape you should have around there. Now, I know most of you did the lab, and so actually let me not be lazy. Let me just go ahead and pull it up. I'm trying not to have too many screens open, but you know what? I think the internet has been good today, so we can segue a little bit. Let me go find the one that has the shapes. So I'm thinking it's this one here, where I posted the extra. Yeah, this help document right here. So you want to have this close to you so that you can actually refer to it and look at the molecular geometry. When you're asked for a shape, that is the information they're asking for. So it does help if you actually have this by you. So you see why I have all these documents and stuff? My desktop is a mess. It's just part of the trade, the things I do. Okay, let me open this and see. Okay, there it is. So this is a document I gave you guys to help you figure out the different shapes, right? So when you go through here, I show you how to count the different groups. So I'm just segueing to show you how I figured this out. I gave you water as an example. Once you draw your Lewis structure, you have to draw your Lewis structure, right? So you can have a visual. This Lewis structure here of water is surrounded by four groups. Now I've labeled the groups, but since I'm here, I want to go ahead and count so y'all can see. And the table I gave you below provides you everything you need. This is one group, the second group. So each lone pair, the two dots, count as a group. So I have two groups here on top, and then these are two groups on the bottom. So we have a total of four groups around here, okay? That's how you count the groups. So back to what I was doing, I was looking at alkene, and I'm focusing on the carbon on the left carbon of the carbon-carbon double bond. I can see right here, oops, I need to write with this. I have three groups, one here, and one here. So how do I use this table on the right to figure out what the shape is? Please note where it says molecular geometry. Molecular geometry is also the shape. Okay, so this is the shape of the molecule. So I scroll down here and I see, I just counted the carbon is surrounded by 3 groups, right? So I get to pick from the 3 group row. I have 2 to pick from. So I want to do some more investigation. Number of bonded groups, 3. Yeah, all 3 groups are bonded groups. I don't have any dots attached to my carbon. So all 3 groups are bonded groups, right? So number of groups, 3. Number of lone pairs around the carbon, 0. I don't have any. So all the other information I need about this carbon, I just have to read across. If they ask me for the electron pair geometry, I'll just write trigonal or triangular planar. Okay, the book either uses trigonal, so I'm going to write that word here. Why do they not stick to one word? I don't know, but trigonal or triangular. Or there's some books where they're a little lazy and they just say planar. So you want to be aware, right? Trigonal or triangular planar. Planar just means the molecule is flat, okay? It's not raised up in the middle, so it's flat. You have an aluminum in the middle, and there's 3 bonds coming from it, and they all lay flat on the table. That's what planar means. So I'm going to look at this shape right here. The shape around that carbon is trigonal planar. If they ask me about polarity, y'all know that's going to be nonpolar, right? Okay. So I'm going to go back to this. I'll leave this page here open just in case. Let me scroll this down. This is how I end up with so many pages. Okay. So that's my situation with the carbon on the left. This is going to be trigonal planar. What about the carbon on the right? Same thing. 1, 2, 3. Okay. Also trigonal planar. And the way the trigonal planar looks, if you're trying to look at the shape, it's pretty much what they have drawn here. Okay. In trigonal planar, you have bonds arranged about 120 degrees away from each other. And that's how they drew it here. So if you did your lab already, great. If you haven't, the lab that says draw the 3D shape, the 3D shape will look like this. Okay, I'll label this as a 3D shape where you have, you know, the bonded groups arranged about 120 degrees away from each other. So equally spaced. They don't have to be exact, but this picture here is emphasizing that they're spread out. And the whole idea of Vesper model is saying that the bonded groups are made up of electrons. Electrons are negatively charged. So all of these are essentially electrons. So are the lone pair groups, right? Electrons are negatively charged, and we know that like charges repel. Okay? So if like charges repel, these electron groups will repel each other so that they can be comfortable. So this pushes against that, that pushes against that, and they all push against each other, and then they kind of resolve to being as far from each other as possible. So right before we were social distancing, these electron groups were social distancing, right? Now with them, it's not a 6-foot distance, it's a 120 bond angle distance, right? And that's where they're most comfortable. Because they have a like charge, they can't help but repel each other, okay? And that's why they have that arrangement. So moving on, all alkenes will have a general formula of CnH2n. Now, I discussed this yesterday, and you will see in this class, we're always building up on what we learned before. We're going forward and then going back, and then kind of forward and back and forward and back. We are recapping, and then we're seeing into the future. So you can judge an alkene if you don't have a picture by the formula. With the formula, the N here will be either 1, 2, 3, or whatever, up to a million. And then the 2N will always be, of course, being 2N. The number you have in front of the hydrogen will always be double the number in front of the carbon, okay, for an alkene. While we are here, I want to remind you, we also saw this general formula also works for cyclic alkanes, right? Those cyclic alkanes, to make them a circle or to make them a geometric shape, we had to drop off 2 hydrogens. And so this formula here works for alkenes and for cyclic alkanes, okay, while we're here. Okay, So as we're looking at alkenes, we've seen what alkenes looks like. With alkynes, the YNES, we have ENES. These alkynes tend to have the carbon triple bond. If the lowest structure is drawn, this is a lot easier. All you have to do is find a triple bond somewhere in that structure, right? So they show you triple bond right here. That means the triple bond is held between two carbons. It's got to be two carbons, nothing else. They give you an example here of an alkyne, acetylene. Acetylene is used by welders. That's the fuel they burn in their fuel torch thing that they use. I've forgotten its name. When they're using the torch to melt metal and stuff and weld things together, this is the gas they're burning. Okay, and it produces that blue flame and it's very, very hot. Yeah, that's acetylene right here. Okay, so we know acetylene is going to be linear. So when they're asking you what is the shape around the carbon-carbon triple bond or each carbon, you're going to say each carbon is linear. How do we get that? Once again, to get this shape, to read that chart, you have to identify how many groupings, how many groups of bonds do we have around carbon. I'll pick one carbon. Let me start with the left. This left one here. This is a group, and this is a group right here. So two groups, right? Because they're grouped together. As a student, oh my goodness, I get so fixated on words, right? As a student, the teacher kept saying electron groups, and all I kept hearing is bonds. Like she or he was saying groups, I'm hearing bonds. They say group, I'm hearing bonds. So I was looking at this, okay? Listen, no shame, no shame. And that was my journey. That was my process, right? I was looking at this as three groups. And so the teacher is saying groups, and I'm hearing bonds. So eventually I said, okay, group together, like a group. Yeah, I get it. Weird. Anyway, so right. These are grouped together, right? And if you're looking at the dots, the electron pairs, two dots make one group. So we just have two groups here. We can now move and look at that little chart, which I have down here. Let me bring this up. Okay, look at that. We have the central item to the left that has two groups. We only have one row to pick from, so we don't really get to pick. This is the only possibility we have with two groups. They even gave you an example, right? When you're looking at the example I gave you here, it won't look just like your molecule. It will kind of look like it as far as the relative positions of the elements in the compound, right? So we also have one central here and then two other ones. So two groups, yeah, two groups that applies here. Are both groups bonded groups? Yes, both of these are bonded groups. Do we have any lone pair? No, I agree. No here either. If that's the case, the bond angle, these groups will stay apart from each other. So the bond angle, the angle between these bonds, oops, wrong place. The angle between these bonds is going to be 180 degrees. Because they're still electron groups, these groups will stay as far as they can from each other. And the farthest they can do is 180 bond angle. So what is our focus in this class, once again, is the shape, not the electron pair geometry. I created this worksheet to help you guys out for all my chemistry classes. So I'm using it with you guys, but I created it for my 1405, 1411, 1412, everybody. So for us, though, our focus is the shape. They really care about the shape, not so much this. In the other classes, they do look at electron pair geometry, okay? So remember, we are focusing on the shape. If they ask you the shape or molecular geometry, you would say linear. I think they have that here, right? Each carbon is linear, right? And of course, well, in ours here, this is nonpolar. It just so happens in this one here too is nonpolar because remember, I mentioned this before, and I'll keep saying this over and over again. Before you know it, you'll be like, oh, I remember that. Carbon-carbon bonds, regardless of whether they're single bonds, double bonds, or triple bonds, are non-polar. Okay? And then the carbon-hydrogen bond is also non-polar. So if all the bonds in the structure here are non-polar, so let me try to isolate them. This bond here, I'll call it NP, is non-polar. This bond here is non-polar. This bond here is non-polar. If everything is non-polar, the whole molecule is non-polar. Okay? And for practical if you need to relate this to your life, if you're like me, and you like to relate this to your life. When I understood what nonpolar was, I related to oil. So this will have behaviors like oil or gasoline, those kind of compounds, right? These are nonpolar. They easily vaporize. You can smell them when you walk in the room, and they have a smell, perfume, cologne, all that stuff. Um, they easily vaporize. If they do have a smell, you easily smell it, most likely a gas, things like that. Okay. Now with the alkynes, the general formula is CnH2n minus 2. Now while we're here, I want to quickly review because while we're learning new stuff, I want to make sure we remember the old stuff. CnH2n plus 2, that was the alkane, right? CnH2n, this is the alkene. We just learned that, double bond. CnH2n minus 2 is the alkyne. Okay. Oh, look at that. We're making more progress this time. So they want us to convert each condensed structure to a complete structure with all the atoms and bonds drawn in. Okay, so you see, I want to say, okay, I can have an opinion about this, that chapter 10 was the one that should have had the greatest shock, because as far as the greatest shock factor, because you're seeing things for the first time. For chapter 11, it will be a little bit like a deja vu. We're doing what we did in chapter 10, only it applies to different kinds of molecules, right? Now we're trying to draw this out and show all the bonds. So let me see. Let me zoom in so I can see. Remember, I mentioned this before. The CH3, these are those end pieces. And then the CH2, or the ones that have less hydrogen, are the middle pieces, right? I should say inner, not necessarily middle, but just not end pieces. So these are the inner ones. If they have less hydrogen, they're in the middle. If they have more hydrogen, they're in the end, right? So the least hydrogen means they're further inside. So I want to make sure that these are on the end. So I'm going to count this as a middle, 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 with these on the end, right? Okay, so I'm going to draw my middle carbons. I have, let's see, 1, 2, 3, 4, 5, right? So 1, 2, 3, 4, 5. And the good thing about you guys coming back, as I'm teaching, I'm thinking about different ways to explain the same thing, and hopefully you're hearing it differently and it's making more sense. Okay, so on carbon 1, I have these two CH3 groups attached, right? Because these have to be on the end. So I'll put one here. CH3. I put another one here, CH3. So I'm done with these. Oh, I can't forget, this H belongs to carbon 1 also, so I'll put it up here. Okay, carbon 2, oh, it doesn't have any H on it. It just has a triple bond. This is my carbon 2. This is carbon 1. Triple bond here. Okay, I'm done with that. Carbon 3, just has this connection here with carbon 4, no hydrogen. I'm good. And I'm done with the triple bond 2. Carbon 4 has 2 hydrogens. I put one on the top and bottom. Top, hydrogen, bottom, hydrogen. Oh, I'm done with that. Carbon 5. This has 3 CH3 groups attached to it. So CH3, this is carbon 4, CH3, CH3. This is carbon 5. Okay, I'm trying to break it down in such a way that it makes sense as I'm doing it. So you're not just following along, but you're seeing how I'm going from. It's kind of systematic, right? I'm trying to show you. So when I itemize this, remember, I have to isolate the CH3s to be the end pieces. So that helps me to see what's in the middle. And when you're drawing this out, you want to draw the middle ones first, and then you attach all the ones around it. Okay? I think I got it. I think I got everything. Good. I like to congratulate myself. I don't know why, it just makes me feel good. Okay, here, next one. For this one here, because these structures are big, I have to add a lot more pages. That's okay. I've never taught this class live, so this is all new to me. I usually just teach it on campus on the board. Okay, let's see. I mean, live online. Yeah. Okay, with this one here, same thing. And it's been like 3 years since I taught it on campus too. So, okay. Once again, the CH3, these are the end pieces, right? And then the ones with the C's with fewer H's are the ones in the middle, or yeah. So remember, these are the end pieces. So I'm going to skip over this for right now. I'll call this carbon 1. This is 2. Oh, there's 2 of these. So this will hold 3 and 4. Okay. Notice there's 2 of these right here, right? So let me write my 4 carbons. 1, 2, 3, 4. Okay. So carbon 1 has these 2 groups attached to it. It has 2. Let me erase that. It has 2 of these CH3s. This is carbon 1. So I'll put a CH3 here, CH3 here. Okay. So I've drawn this. I've drawn this. I have to include the double bond. There's a double bond attached to carbon 1 and carbon 2. Okay. Carbon 2 also has an H attached to it. So I'll put this up here. Okay, this is carbon 2, carbon 3, carbon 4. Okay, this part here, let me erase it so y'all can see this better. This part here is just telling you that there are CH2s, 2 of them back to back, but this person ultra condensed it and then just erased 1, right? To write it like that, like shorthanded. So we're just opening back up and saying this is essentially 2 CH2s back to back, right? So I'm going to draw that here. That makes my carbon 3 and carbon 4. So carbon 3 here has got 2 H's up and down. And my carbon 4, same combination, up and down. So I have to connect these with 1 bond. And then finally, I have this last one. I'll just add right here, CH3. I mean, you can spread it out even more. I'm just showing you guys how, how I do that. If you want, you can spread this out more and then, show all the bonds of all the side ones. To me, this is sufficient. Okay. Let's see. Last one. This one here. Oops. Copy that. Oh, I'm going to need a 3rd page. Okay. Once again, it looks like, well, I can't start here. I want to start here, but I can't really start here because I can't just draw the double bond. So because the double bond is here, I'll actually start on this as my carbon 1, okay? I mean, I could start here, but it would look very weird. So this would be my carbon 1, carbon 2, and carbon 3, okay? So I have 3 carbons. Since there's a hydrogen on the right, it looks like I have an oxygen as a central atom too. So I'm going to write 1, 2, 3, 4, but my 4th central atom is an oxygen, not a carbon. Okay, since the hydrogen is attached to the oxygen has to also be in the middle. Okay, with the rules, it's very difficult to explain all the rules. I feel like you learn it as you're working on it. So I'll draw my 4 central atoms. Carbon, the first one, carbon, the second one, carbon, the third, my 4th atom is oxygen. Okay? So between carbon 1 and 2, we have a double bond. Right? Carbon 1, I've drawn that. It also has 2 other bonds with hydrogen. So I can do this up and I can write this left. Okay? Carbon 2, I've drawn that. Carbon 2 is also bonded to hydrogen. I'll draw this up here. This is done. Carbon 3, I've drawn the single bond, is also bonded to 2 hydrogens, up, down. And then we have oxygen, which is also bonded to a hydrogen. And don't forget, with oxygen, you have to bring in those 2 lone pairs, right, to make it an octet. So hopefully you're seeing, we're not using the regular Lewis process to draw this. I'm just spreading it out, right? It went from the condensed form to the form where you show all the bonds, going by the way this is. So hopefully this makes sense as you look at it. Okay, I did open this page. I don't really need it. Delete it. Okay, next one here. Determine the molecular formula. Okay, determine whether each molecular formula corresponds to a saturated hydrocarbon, an alkene, or an alkyne. Chemists like to remix words. So I tell people you have to know more than one way of describing something. They could have said here, alkane. right? They didn't. They said saturated hydrocarbon. Remember, alkane is the one that has the most number of hydrogens. So they're asking, is it an alkane? Remember, CnH2n plus 2. Or is it an alkene? CnH2n. Or alkyne? CnH2n minus 2. Okay, so we're going to compare these, right? The easiest one I like working on is the alkene because all you're looking for is the second number being double of the first, right? So I look at this first one here. 3 times 2 makes 6. So 6 is double of 3. So definitely alkene, right? This is not double. This is not double that. This is double that. So this is definitely an alkene, right? I mean, I'm like, if I can do that, why not? Nobody's stopping me from that. It's not illegal. I can do that. So it eliminates, I'm done with the alkene. It's done. Now I can look for the other ones, the alkynes or the alkanes. Let me start with the alkane. So for the alkane, whatever number the first one is, the N, the second one has to be double and then plus 2. So let me see. 5 times 2 is 10, plus 2 is 12. Yep, this is an alkane. 8, I can do the math here. 8 times 2 is 16, right? I'm checking to see if it's an alkane. Oops, I wrote too slow. Hold on. 8 times 2 is 16, plus 2 is 18. So if this is an alkane, this would have to be 18. So it's not an alkane. Let me check to make sure it's an alkyne. 8 times 2 is 16. Minus 2 is 14. Oh, okay. So this is an alkyne. All I'm doing is I'm doing this math right here to figure out what this number is. Okay. Okay, so we're now moving on. Once again, we're learning these together. And this is a review of what we did yesterday also. Because remember, alkenes and alkynes are composed of nonpolar bonds. So are alkanes. This applies to alkanes also. So alkanes, alkenes, and alkynes are composed of nonpolar bonds. Okay? Their physical properties are like those of alkanes. Okay, because they're nonpolar, alkenes and alkanes, right, have low melting points, low boiling points, and they're not soluble in water. Because remember, they have oil-like properties. They behave like oil. So with oil-like properties, they are not soluble in water. Okay. Now, unlike alkane, so remember alkane has the most number of hydrogen. So here with the most numbers of hydrogen, this is called saturated. Alkenes and alkynes just don't meet, they're not able to have the maximum number of hydrogens. So these are called unsaturated. Okay. Unsaturated because they haven't reached that level of maximum. They don't have the most hydrogens possible per carbon. Okay, so less than unsaturated, maximum amount saturated. Okay. Okay, what are we looking at right now? Oh, we've seen the condensed structure, right? So they're just showing you how to write the condensed structure. If you want to condense this structure, you can write it into this form right here. So they're showing you there's so many different ways. Let me just write it down here. This is a central carbon. I like to write that down first. So you have a choice. You can write, based on the way this is written, I would actually put the CH3 outside and then the H inside, just like what they did right here. Because you have to write both CH3 and H around C so that you can communicate that both these are connected to C. Okay? Then you have your double bond here. You can't condense the double bond because the other person cannot assume. But you know what? I have seen some books where they have left this out like this, and then they've written C and then H2. So what I did then to figure it out, I was like, wait a minute. This carbon here has an unusually low number of hydrogen. Being a middle one, it should have CH2, right? And this right one should be at CH3. But each of them is missing one hydrogen. If they are missing one hydrogen, each of them, that means somewhere in here is a multiple bond. So even though they're telling you keep the double bond here, don't believe them 100%. I have seen some other books. The authors of the books don't follow the same rule to a T. Like I want to get them all in one room and say, people, make my life easier. It doesn't work that way, right? The author makes a difference in how the book is written. So sadly, we have to learn multiple ways. It's kind of like being bilingual within chemistry, right? So they're telling you here they want you to keep the double bond. Okay, here, same thing. If you have the situation here, you can eliminate the single bonds, that's fine. But once again, I have seen some books eliminate both the single bond and the triple bond just because they can. And you have to adapt, right? So of course you can see right here the single bond was eliminated. Now if they eliminate the triple bond, it will look like this: CH3, C, CH. And of course when you look at that, you're saying, regular middle ones, if they have single bonds, look like this. Regular end carbons look like this, right? So from here you can see this is missing two hydrogens. This one here is missing two hydrogens. So for every two hydrogens that are missing, we get a second bond, right? Also missing two hydrogens. You may not encounter this, but I was looking over some of you guys' labs and stuff, and I saw things like this. The author of the lab is completely different from the author of the textbook. They may not even know each other. So they don't necessarily follow the same rules to a T. Okay, here we're working on scenarios. So they want you, like a puzzle, to it says give the molecular formula for each of the following compounds. Oh, molecular formula. Oh, okay. I thought I was supposed to draw. I can do it right here. Alkene. Okay, I just like to write the formula here. CnH2n plus 2 for alkane. I'll just write A and E. CnH2n for alkene, E and E. CnH2n minus 2 for alkyne, Y and E. Okay, they want an alkane that has 4 carbons. So, alkene, that's this one here, right? Alkene. So it has to follow this format. Okay, I'm just going to substitute here. It's going to be C4H8, right? For the alkene. Okay, check. A saturated hydrocarbon, they mean the alkane, that has 6 carbons. So we're dealing with this one here. So we're dealing with CnH2n plus 2. I'll just draw it on the side. So N has to be 6, right? So N is 6. So C6, 2 times 6 is what? 12 plus 2, 14. I'm smiling because I'm beginning to panic. I'm like, oh no, I have to add. I can do this. We do complex math in my other class, and then when I have to add, I'm panicking. So C6H14, right? 6 times 2 is 12, plus 2 is 14. Okay, I feel a lot better. An alkyne that has 7 carbons. So we're dealing with this alkyne, CnH2n minus 2. Now, N is 7, right? So C7H 7 times 2 is 14, minus 2 is 12. It does help me feel a lot better if I write it down, right? Okay, an alkene, CnH2n, that's the alkene. That has 5 carbons, N is 5. So this would be what? C5H10. As I said, mathematically, my favorite is the alkene because it's less math. Okay. And look at that. By the time we got to naming in yesterday's chapter, it was like towards the 2/3, right? Here by slide 11, we're already at naming because all the other stuff we learned applies here. Okay. And what we're going to do here is we're going to name both the alkenes and the alkynes at the same time. We're going to learn both because whatever rules we're looking at applies to both, right? So trying to consolidate. Okay. On the left, we have the alkene. On the right, we have the alkyne. Okay, so just like we did yesterday, you have to find the longest chain, but this time it's not just any longest chain. Find the longest chain that contains both carbon atoms of the double or triple bond. So you want to find the longest chain, but the longest chain has to have the double bond. And it has to contain both of the carbons holding the double bond. That means you can't count from up here and go left and say that's your longest chain because you left out the carbon-carbon double bond, right? So here, let's see, you start from the left and then go to the right, okay? Now, yesterday I was asked, do you always start left? You try to get to the start on the side that has the double bond closest to the edge, okay? Because they're trying to get the double bond very quickly. They want to assign the double bond a small number. So right here, this will be our longest chain. And when we're numbering our carbons, this will be carbon 1, 2, 3, 4. Okay? Let me erase it so it's not in the way. Yeah. And then over here, let me see. Same thing applies for my alkyne. This is going to be my longest chain. But because of where the triple bond is placed, I have to start counting from the right. Okay? 1, 2, 3, 4, 5, 6. Just like what we did yesterday, only yesterday we didn't have a triple bond. Yesterday we're trying to get to the side group faster. Today I'm like, forget the side group. The focus right now is the double and triple bond, right? We will get to the side group when we get to it. Okay, so there. So we've selected our longest chain. We already numbered it. We weren't even asked to do that yet. Okay, once we have the longest chain, it says, since the compound is an alkene, change the ane from the alkane. So they're trying to say, since you already know how to name alkanes, name it as though it was an alkane, right? That's what they're saying here. Name it as though it was an alkane, but replace the ane with the ene. So that suffix, like the last name. So this carbon here, now we're back to the structure here. The alkene, it has 4 carbons, right? 1, 2, 3, 4. In our prefixes, but was 4 carbons. So if it was an alkane, you name it butane, but replace the ane with the ene, so butene, okay? We're not done. We have to describe the location of the double bond because remember, the name we end up with, that's kind of like the charades name I was telling you about. When somebody else sees the name, they will be able to redraw the structure. And the goal is for the structure they draw to look just like this one. It won't be exact, but it will follow the order and the connection. Okay? So we want to be very explicit when we're describing this. Okay. What about this one here? Now we're going from right to left, right? 1, 2, 3, 4, 5, 6. We have 6 carbons. So 6, the prefix for that is hex. Hexane, if it was an alkane, but we're not dealing with an alkane, we're dealing with an alkyne, so hexine. Okay. Okay, so then we move on and okay, finally the number. As I said, we have to say which 2 carbons are holding the double bond. So what they do here is, since we're counting from the left for the alkene, you're going to put the number 1 to say that the double bond is attached first to the first carbon. They don't write both numbers, they just put one number. That's just the rule. I don't know why. That's the rule we follow blindly. Okay? So the double bond is attached first to carbon 1. For that reason, you will write here 1 dash. Remember the dash? Between a number and a letter, you have to have a dash. Yeah, so 1 dash butene. So when I see this, I see, okay, ENE, that means double bond. And then this one here means 4 carbons. This one here says on first carbon. So we have a long chain that has 4 carbons, but there's a double bond on that long chain and it's on the first carbon. Okay, the name is very systematic. And then here we're still dealing with the longest chain. Over here, once again, 1, 2. So the triple bond is assigned to the first carbon holding it, not the second one. So we see 2-hexyne. We have a triple bond in a 6-carbon long chain. The triple bond is of the second carbon. Okay, so this is describing this part right here. Now we're finally going to deal with the side group. It says name the compound using the first number assigned to the multiple bonds. So here we are. Now we're moving on and finally getting to the side group and adding that in. We already did this part here, right? So just like we did yesterday, if the side group has 1 carbon, guess what it's called? Methyl. That part hasn't changed. All side groups end with "-il". I know. So methyl, propyl, ethyl, butyl. So if it ends with "-il", it's a side group. Okay. So in our case here, since this is 1, this is 2, this is 3, our side group is technically 3-methyl. So when you combine it here, it becomes 3-methyl-1-butene. Do you see all those dashes? Yeah. You have to include every dash. When I was taking this class, man, I will forget the dashes and my teacher will mark all over, just red, red everywhere. I'm like, my goodness. Arrows here, arrows there. You're doing it wrong. Yeah. All those little pieces, right? Remember, between letter and number, you have to have a dash. Have a dash. Dash, right? So over here, let's see, our numbering was 1, 2, 3, 4, 5, 6. So we have 2 carbons. It's still called an ethyl group, and it's in position 4, carbon 4. So 4 dash, ooh, I almost forgot. 4-ethyl. If I forget, y'all please remind me, okay? 4-ethyl dash 2-hexyne. Between every letter and every number, there has to be a dash. Okay. So they assume that we are ready, right? We are ready to name our own compounds. Let's look at this. So let me look at this right here. That's my longest chain, right? I think it's my longest chain. So I'm going to erase this so I can see. Let me use the highlighter because I can still write on top of that. Okay, that's my longest chain. I will number from my left because my double bond is closer to the left. So 1, 2, 3, 4, 5, right? 1, 2, 3, 4, 5. Okay, so if I have 5 carbons and this is double bond, that should be pentene, right? 5 carbons with a double bond. Where is my double bond placed? It's attached first to carbon 1. So I'll put 1-pentene. I'm about to write something else in front of it, so I'm going to just put the dash there, okay? I do have a side group. This is the methyl group. My methyl group is attached to carbon 3. Okay, so 3-methyl-1-pentene. Yay. Okay. Once I figured this out, I'm like, ooh, nobody can stop me. This is how it's done. And I get excited. Anyway, once I figured it out, until I figured it out, I was like, oh my goodness. Will I ever figure this out? It's not that bad. You're following the pattern, so you're following the similar pattern all the time, right? Ooh, look at this. In parentheses, and there's 2 of them. So we have to decode the structure. We can't try to name it like it is, right? We have to simplify so we can select the longest chain. So I'm going to redraw this, right? Like this. See, starting with this, double bond, C, H, CH2, CH2. Let me do this because it helps me to keep track of what I'm doing. Okay, CH2, and then let's see, I've done 1, 2, 3, CH3, right? So I have this side copied over. I have 4 carbons on the right. Correct. Now I need to decode what this is. Since it's saying this carbon right here has 2 of these groups attached, I'm going to attach one group right here, CH3, CH2, and then where do I write the other one? Do I have enough space? I'll do it up. I'll write it up here. There. CH2, CH3. Okay, so what I did here was just decode this. You don't want to try to name it when it's so condensed, right? So decode that so we can see that. Okay, I think I did everything. Now I can go ahead and find my longest chain. I think you can see now your longest chain goes from here all the way to there. That's my longest chain. Let's see, numbering from the left, right? 1, 2, 3, 4, 5, 6, 7. This would be 3 or 1, 2, 3, 4. No, from left is better. 1, 2, 3, 4, 5, 6, 7. So if I have 7 carbons, that's going to be what? Heptene. Because it's a double bond, right? Heptene. Okay. And my double bond is on position or carbon number 3. So 3-heptene. Do I have a side group? Yes, this one here. This is on carbon 3, so it's 3-ethyl. So 3-ethyl-3-heptene. Okay? Yeah, follow the same pattern. And then here we have, oh, okay, let me see. When I start getting into the questions, it gets so exciting for me at least. So I'm like, okay, I need to pick out the few questions. So let me work on this one here and then we'll continue. Because I want to do a few of these and then continue the rest of this. Okay, I will work on this. Once again, this part I think is okay. The tricky part is this part here. So I'm going to copy 1, 2, 3, 4, 5, 6. So CH3, 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 oh, CH2, CH2. The middle ones are CH2. CH3, CH2, 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 the fifth one, right? 1, 2, 3, 4, 5. C, 6, 1, triple bond. Now I'm done with that. C, C here. Then this is attached to 2 CH3s, one right here. I'll draw the other one above, CH3. And then there's a hydrogen also there. So now I have my complete structure. So this will be my longest chain. Okay. I have to number it from right to left because that's the quickest way to get to the triple bond. 1, 2, ooh, hold on. 1, 2, 3, 4, 5, 6, 7, 8, 9. Ooh, 9. 9 will be, do I have room on here? I'll write up here. Octine. No, sorry. 9 is no 9. Oct is 8. No 9. No 9, right? I know that's a weird name. No 9 is 9 with a triple bond. And then the triple bond is on carbon 3. So it's going to be 3 dash. So I'm done with this part. And then we have a side group. This is going to be methyl. And our methyl is attached to what carbon? The second carbon. So 2 dash methyl dash 3 dash no 9. Okay. So I'm not going to work on this part because it's like the rest. And this is not really that complicated. As far as you didn't have a super condensed structure, right? I want to go and I want to pick a couple of these. Let me do the one that is kind of convoluted, these two right here. Okay. Hold on. Where am I working right here? Okay. So work on this one first. Okay. Then I'll work on the next one. Okay, so for this top one here, I start with the word far right, heptene. So 7 carbons with a double bond. 1, 2, 3, 4, 5, 6, 7. C1, C2, C3, C4, C5, C6, C7. There's a double bond. Okay, where is it located? On carbon 2. So between carbon 2 and 3, they need to have a double bond. These can all have single bonds. Okay, so this part is done, this part is done, this part is done. And then on carbon 2 also, ooh, I have a methyl group. So on carbon 2, I have a methyl group, right? So this is done. And then I also have an ethyl group on carbon 5. Where's carbon 5? Carbon 5 is right here. I have an ethyl group. Ethyl group has 2 carbons. So this is going to be CH2, CH3. Okay? So the rest of it I just fill in. I put an H here, 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 fill in the H's to make the carbons have 4. 1, 2, 3, 4. I need one more here. This one is good. I need one here. I need one here. I need one here. This is the structure. Okay. And then I work on this last one. Hex, ine. So hex is 6 carbons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I have to number these. It helps you out and it helps me out because I have major focus issues. It doesn't take me much to get distracted. Okay, so I have 6 carbons, right? And carbon 3 has the triple bond. So carbon 3, triple bond. Okay, so I've done the 6 carbon part. I've drawn my triple bond on the 3rd carbon. Now it says I have a methyl group, but I have 2 right? 2 methyl groups. So these 2 methyl groups are on carbon 2 and carbon 5. So on carbon 2, I have a methyl group, but I also have another methyl group on carbon 5. And that takes care of these. Okay, so fill in the rest, whatever is missing. I can actually go, I mean, I'll leave the numbers there because I need them. I really don't, but I'll just leave them there. So I fill in the bonds, right? 1, 2, 3, 4, 1, 2, 3, 4. This one already has 4. This has 4. This is missing 1 bond. Okay, H, H, H. H, 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 H. If you want, if the numbers are distracting, you can remove those because they're done with their purpose. But yeah, okay. So now we're moving on to cis and trans. Now I know you have done a lab that has to do with this cis and trans, but we're now learning it in context. So cis and trans isomers, these are called stereoisomers. So they're called stereoisomer, which is different from the constitutional isomer, right? So while we're talking about isomer, I want to do a quick recap. For the isomers that we have talked about so far, we talked about constitutional. These are the kind where they have the same molecular formula, but different arrangement. So I would just say different. Let me try to be a little extra, but very different. Like you have to count to make sure they're the isomers, okay? Constitutional. As we look at the cis and trans isomers, these usually look the same. No, they don't look the same. They look similar. They look more similar. Stereoisomers. Stereoisomers. These are different in their spatial arrangement. So the difference here, of course, they have the same molecular formula, but different spatial arrangements. So what I mean by that here, the difference in the spatial arrangement is brought about by that double bond. Okay, so we tend to see cis and trans isomers with double bond molecules, not triple bonds. Okay, so we only see it with double bonds only. So for example, If you draw the regular condensed structure of 2-butene, this is what it looks like. But in reality, the 2-butene has two possible, as it says right here, arrangements. These arrangements can have the CH3. So everything is happening. All this action is taking place around that carbon-carbon double bond. Okay, this is where we see the cis and the trans formation right here. So let me highlight that because we're focusing on this. Around the carbon-carbon double bond, these two large groups, they're considered large because you see they have more atoms. There's one carbon, three hydrogens, versus on the opposite end, across the double bond, you have one hydrogen, right? So if you have the two large groups on the same side, these are considered large. They're large in size, they're large in mass, they're large in more atoms. You have two large groups on the same side. Since they're on the same side, they're called cis. So when I was in school, right, my teacher was saying cis same cis, and I'm looking at him like he's special. Guess what? I started saying same cis, and what I would do is I would hold both my hands up, like like you're waving your hands in the air, and if both hands were up, like you're trying to show a V sign, give me a V. That was cis, and then trans. I know. Y'all gotta get to know me. Trans is like, this reminds me of, what's that John Travolta dancing and he has one hand up and other hand down versus the V. So it's almost like the YMCA thing, only this is not YMCA. This is more like a cis trans movement. So when you have these large groups diagonally across from each other, this is considered trans. So trans is opposite, and the reference point is double bond. Trans molecules have the large groups opposite ends of the double bond. Cis molecules have the large groups on the same side of a double bond. They can be both up or both down. Trans have to be opposite, so kind of diagonal. Okay? So you have the cis isomer, the cis version, cis isomer, trans isomer. So when you have isomer compounds, the name is the same except for the descriptor. Look at this one here. These are cis and trans of each other. The 2-butene part matches this exactly. The only part of the name that's different is the descriptor that tells you where the large groups are. So cis dash, remember, between letter and number, you have to have a dash. So cis dash 2-butene, and then trans dash 2-butene. So you can quickly tell two isomers are cis and trans of each other, or they are stereoisomers, because the only difference in their name is the cis and the trans. With the other isomer, the constitutional isomer, the whole name may be different because it's a little bit more complicated than what it seems, right? The connectivity is completely different. Okay, so like we saw right here, once again, you want the two large groups on the same side to make it cis or trans. To make cis on the same side, trans opposite ends, right? So I won't spend a lot of time here. Oh, in this structure here, they're telling you this molecule is exactly like this molecule. First of all, you can't have cis and trans when you don't have two large groups on the same side. So you see how this is missing the word cis or trans? Because this is not large. This and this are the same size. This would have to be larger than that for us to have cis and trans. But since it's the same element technically, then this is neither cis nor trans. Okay? Essentially, to have cis or trans, you have to have a large group on one side and a large group over here, then a small group, and then a small group. And this will give you cis, right? And then for trans, you're doing the opposite, or diagonally, right? Large, you got small, and then you got small right here. This is trans. But if you have this scenario we have here, double bond, and then you got large, and you got small, and you got small, and then you got small over here, that does not meet the prerequisite of cis and trans. So it either is or it's not. There's no in between here. Okay, so this won't work out. Okay, so then we're gonna compare, right? So you can see here, first of all, the easiest way is saying, okay, hold on. Stereoisomers are a new class of isomers, as a new in the progress of us learning. Stereoisomers are isomers that differ only in the 3D arrangement of the atoms. Constitutional isomers, the one we learned before, differ in the way the atoms are bonded to each other. Here we have a greater difference, right? Okay, so let's see. When we're looking at this here, imagine the names weren't provided, right? Imagine this part was not here. But then you have this arrangement. As usual, find your longest chain. I'm going to use my highlighter to highlight the longest chain. This is my longest chain right here. And my longest chain has how many carbons? 4. So this would be butene. Okay. But when I number it 1, 2, 3, 4, where's my double bond? Carbon 2, so 2 butene. But because of the special hands up arrangement, this has to be called cis dash. Okay? And then you have this other one here, same thing. Find the longest chain. It goes from here all the way down here. Okay? Number it. 1, 2, 3, 4. Where's the double bond? Oh, I forgot to name my longest chain. Butene also. Okay? 2 butene carbon, right? And then because of the large groups being opposite to each other, you have what I call the dance move, right? Dancing fever. Anyway, you have the diagonal arrangement. This is going to be trans. Right there. Okay. Once again, cis and trans isomers, the only part of the name that's different is the descriptor or the word that describes the position, cis or trans. So what's going on with this one here? With this one here, I find my longest chain, and it has 4 carbons. So I agree. This is going to be butene. But where is my double bond? If I do it from the left, 1, 2, 3, 4. My double bond is on carbon 1. That makes it a different compound completely, right? So it is butene, and it does have a double bond. My double bond is in a different position, and then you see it's neither cis or trans. So what we can say here is, I'm going to give these letters. Let's say my first molecule is A, my second one is B, and then C. A and B are constitutional isomers, just like what they showed over here, right? They're constitutional because even though they have the same molecular formula, same number of carbons, same number of hydrogens, they're connected differently. The double bond is in a whole new location, right? A and C is also a constitutional isomer for the same reason, right? A and C. So they show you right here. A and C. Oh, that was the first one I showed, my bad. And then A and B right here. I am ahead of them or they're behind me. But then B and C, these are stereoisomers because you see their name is alike except for the cis and trans. Okay, so now you're asked to draw this structure here. So I'm going to pick a couple because I'm trying to make progress with this, right? I'm going to pick a couple, draw the structure for each compound. It says cis-octene. Okay. Oh, cis-2-octene. Huh. So you're going to draw 1, 2, 3, 4, 5, 6, 7, 8. Oct means 8 carbon. Ene means double bond. The double bond has to be in the second one. Okay, that's fine. I'll keep recording. Thank you. Okay, you're welcome. Okay, so let's see. 1, 2, 3, 4, 5, 6, 7, 8. So on carbon 2 and 3, that's where my double bond is, right? I need to make this a cis. Huh. Cis means same size. So what I'm going to do here, these remain in the middle. I'm going to move all of these 1, 2, 3, 4, 5 up. I'm going to shift them up. 1, 2, 3, 4, 5. This is 4, 5, 6, 7, 8. Yeah, these will be up here. Okay, let me erase that. I messed this up. That's okay. Let's see. C, double bond C, and then this. They said cis. This is my second. So my first, second, third. Right. So the large groups have to be on the same side. That means on the left of my carbon 2, I need to move that bond and bring it up. See? And then there has to be a hydrogen down here, a hydrogen down here. So go in and fill in all the missing pieces. Each carbon has to be surrounded by 4 bonds. Yeah, 4, 4, 4. This is 4, this is 4. 1, 2, 3. So H, H, H. And then we got H, 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 H. Okay? Yeah, so this is, I know it's an ugly picture, but this is C, cis 2-octene. It's cis, why? Because I managed to get my large groups on the same side. Okay? I'm going to work on this one here. Trans 4-methylpentene. I need more space because I feel like I'm running out of space. So right here, pentene, 5 carbons. 1, 2, 3, 4, 5. Carbon 2 has the ene part. 1, 2. This has a double bond. Okay. Now they want trans. So I'm not gonna erase this time. I'm actually gonna cut. So I'll put this up, and I'll put the rest of this down. See? Ta-da! So that. Okay. So it says 2-pentene. I got that. And then it says 4-methyl. So I need to finish numbering this. This is 1, 2, 3, 4, 5. So the 4-methyl on carbon 4, I have a methyl group. CH3. So here I have a H. Here I have a H. I have a H. So I'm going to fill in the H's now. 1, 2, 3, 4. Here I have a H. Here I have a H. Here I have a H and H and H. Fill in the carbons. Make sure each carbon has got 4 bonds, right? 4, 4. I think I got all the hydrogens in there. So this is trans. Why is this trans? This is trans because I made sure my large groups on opposite ends. So that's trans 4-methyl dash 2 dash pentene. Correct? Yep. Okay. Okay, but this one here says, label each pair of alkenes as constitutional isomers or stereoisomers. Here's the thing. You could draw it if you want, or you can try to name it. Like, let me start with the easier one, okay? With this one here, large groups on the both sides, on the same side, large groups on the opposite end. Let me make sure I have the right number of carbons, first of all. I'm jumping the gun. It does look like a cis and trans isomer, right? Let me see. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. Oops, I pressed something here. I got too excited. Hold on. Okay, with these two on the same side. So this is definitely a cis and trans version of the same molecule. So these are stereoisomers. This one here, I can draw the Lewis structure if I want, but before I do that, you want to check. For cis and trans, the carbons have to be in the same location, attached to the same carbon, right? Sorry, the double bond has to be attached to the same carbon. Over here, look, my double bond was attached to carbon 2. See that? Over here, same thing, carbon 2. Let me see, counting from left, 1, 2. This is attached to carbon 2. Counting from left, 1, 2. This is attached to carbon 1. Ah, there it is. It's constitutional. Constitutional. Because They were not attached. The double bond is not attached to the same carbon. Let me see. I have one, two, three, four, five carbons here. I have one, two, three, four, five. So this is what? Pentene, pentene. But on the right, the pentene, the double bond is attached to the first carbon. On the left, the double bond is attached to the second carbon. Two pentene, one pentene. Sorry. Oh, my ears are blocked. I think it's just allergies. Okay, so it's constitutional. It failed the test. Double bond attached to different carbons. Okay. Oh, so now we're kind of branching off of alkenes and going to still real life, but application. We're focusing on our health and medicine. So, as I talk about this, I think about food. Okay. Fatty acids. So we're talking about saturated and unsaturated fatty acids. You know how they say saturated fats are bad for you, trans fats are bad for you? We're about to walk down that lane, okay? No judgment here. They, whoever they are, the people that the government hired to study this stuff, researchers, they say this stuff is not good for you. It does taste good though, right? We got to admit that. Okay, fatty acids are carboxylic acids. Now we talked about carboxylic acids before, right? The R-cool group. This is the one that has the rest of the molecule, carbon number one O, and then hydroxide. We'll get to this again down the road. When we talk about fatty acids, we're talking about the molecules of fat. The molecules of fat are made up of fatty acids with long carbon chains. These carbon chains are about 12 to 20 carbon atoms, okay? So while we're here, I want to mention this. If you have a molecule that has a bunch of carbons, like this, a bunch of carbons, it tends to be fatty. Fatty. Okay? Greasy, fatty. If it's food, it's tasty. Lots of carbons and hydrogen. You can tell from my voice I'm smiling right now. I'm just imagining a really nice steak, right? I mean, just because you're doing chemistry doesn't mean you can't imagine food, right? So we're told here naturally occurring animal fats and vegetable oils are formed from fatty acids. These are natural as you eat animal fats in meats or vegetable oils like, canola oil, vegetable oils. These are naturally formed from fatty acids. So there are different kinds of fatty acids. They're the ones that are saturated. Remember, saturated are the ones that have no double bond, right? These are like the alkanes, no double bond. These have long hydrocarbon chains. Example, coconut oil. Oh, so let me tell you a little story, right? I started watching my calories and counting them and entering them in this app called MyFitnessPal. And then I cooked some coconut rice, okay? So coconut rice is the thing where I come from. Oh, it smells so good. The flavor was so good. Then I logged it in and it said this food is high in saturated fats. I'm like, you know what? It tasted good. It tasted good. So of course, the next time I ate it, I ate less. Because the way MyFitnessPal works, if you've ever used the app before, it has a limit based on the desired goals you have. It has a limit on what you're allowed to eat per day. Of course, you're free to violate those limits, right? But that coconut milk I used in the rice made it so aromatic and flavorful. But as soon as I logged it in, it gives you a message. Food high in saturated fat. I'm like, thank you very much, ma'am. Thank you. Of course, butter. Beef, bacon, cheese, sausage. I'm sorry. I'm not really even that much of a foodie. I just love food. Not really, yeah. Oof. And then the unsaturated fats. So these I would say, okay, these are the unhealthy fats. These are the ones they tell you don't eat too much of, okay, but it's saturated. The unsaturated fats, these ones have one or more double bonds in the long hydrocarbon chains. These are the more healthy ones. Peanut butter, that's good, right? Olive oil, almonds, pistachios, avocado, salmon. Oh, I'm thinking of a sandwich right now with salmon and avocado. Tuna, okay? So these are more the healthy fats. So dietitians are usually encouraging you to eat fats that have a bunch of double bonds, okay? Not back to back, but you get the idea, right? Unsaturated is better than saturated. Okay, so double bonds in naturally occurring unsaturated fatty acids are cis. So when you see naturally occurring fatty acids, this is the good kind. They're cis fats. Okay. I bought a bag of chips recently that said no trans fats. I'm like, okay. So then what fat is present? Because I know there's a fat present here, right? When they're trying to sell you food, quote unquote healthy food, they're usually advertising what's absent versus what's present. What's present is listed in the bag. It doesn't really get a lot of attention, right? Some do a better job of presenting that, but usually you have a cis fat or a trans fat, okay? So we have cis fats or trans fats. Trans fats. And the message here is cis fats are good, trans fats are bad. Okay? So as the number of double bonds in the fatty acid increases, the melting point decreases. What does this mean? So you want to know this statement. This is a very important statement. When you have more double bonds in that long carbon chain like this, I'm going to be a little extra and draw a bunch of double bonds here because I can. I'm trying to make a point. The more double bonds you have, the lower the melting point. That means that this is most likely going to be an oil in room temperature. So they're trying to say to you, if the fat that you're eating is unsaturated and it is so soft, it's like oil, that's better for you than the hard fat, the fat that's hard before you eat it, okay? So fats are generally formed from fatty acids having fewer double bonds saturated. These are solids at room temperature. Once again, the kind of fat that's really hard at room temperature is not very good for you. The one that's oil is better for you. If you have a choice, choose the one that's oil-like or is soft at room temperature. That means it has a lot of double bonds, and double bonds are king. Okay? Oils are generally formed from fatty acids having large number, they're saying over and over again, right, of double bonds. Nobody's paying. This is not advertising. This is just education. Large number of double bonds, unsaturated, and these are liquid at room temperature. So we're still focusing on health. So why exactly is it bad for you though? Saturated and unsaturated fatty acids. Which of these two has a higher melting point? I'll tell you right now. Saturated fats are solids at room temperature and have high melting points. Okay, they're most likely a solid at room temperature. They do taste good though. Okay, I'm just thinking about when you cook bacon and the grease is left over and then it solidifies. When it's solidifying, I'm like, yeah, there goes that saturated fats, right? It becomes solid at room temperature, but it does taste good. Okay, here's an example of stearic acid and here's oleic acid. You can see this right here. This is a fatty acid, right? You recognize the alkene bond, but we're now applying it to life outside of chemistry, so it's called an oleic acid. This is a cis fat, okay? Cis fat, and it's also unsaturated. Why? Because it has a double bond. This one right here, I'm looking for a double bond. I don't see one. Doesn't count. This is a carbonyl group. This is technically a saturated fat, okay? So, oh, they didn't continue to make the point. Anyway, don't worry about it. I'll make the point. I'll land this point down. So, saturated fats are bad for you. These are bad. Why are they bad? I'm going to use just lines to draw it. You see how the saturated fat is all neat and linear? It's saturated fats are solids because of the way the solid can pack. In solid molecules, so I'll say here in solids, molecules are packed closely to each other. You have very little room, right? So these are not little round molecules, they're lines, right? So they're just lying on top of each other like this, but they're packed very close to each other. They produce a dense solid. Now, once again, let's not deny it tastes good, but this is your saturated fat. For your unsaturated fat, these are cis fats, right? So you see how they're shaped? The shape ends up being like this. So when they try to pack closely to each other, they don't even get that close to each other because they have this weird V shape going on, right? Some of them are like this. So they can't pack closely to each other. I'm trying to make a point here, so I'm being a little extra. Do not pack closely to each other. Therefore, they are liquefied. Remember, liquid state has molecules that are not very close to each other. So in the liquid state, molecules, so in liquid state, this is kind of like a review. Molecules are not very tightly packed. You have molecules kind of, they're close to each other, but not too close, right? So essentially that's what we have here. So this is a chemical defense to explain to you why saturated fats, as tasty as they are bad for you because they form dense solids. And these are the ones that go in your body and eventually form plaque, and they cause high blood pressure, diabetes, all the other bad stuff, right? So we work out to get rid of this stuff here. Okay. After talking about food, now we're talking about birth control. Synthetic birth control, these ones here do have sorry. This is talking about synthetic birth control pills. You see how there's a similarity in structure to the female sex hormones, estradiol and progesterone, but these contain a carbon-carbon triple bond. So what they're showing you here is these are the natural female hormones. So I didn't mention this before, but I need to mention this right now so it makes sense why this is important. Okay, so let's take a step back. There is an understanding that the structure of a molecule dictates its function. Okay? So we learn about the structure of the molecule because we're trying to figure out what is the molecule doing. So unlike people where you can't just look at somebody from the outside and the way they look and then judge what they do in life by the way they look, right? That's called prejudice, whatever. You're not supposed to do that. But in the world of science, you're supposed to do that with molecules. As you see the molecules, you judge their function. You can estimate their function based on how they look. What functional groups do they have? What kind of bonds do they have? And you are estimating, you're guessing what kind of function they perform based on how they're equipped, right? So you can see here, these are natural female hormones. So when the pharmaceutical scientist, which, man, my gifting is teaching, not business. But let's imagine a different world, right? A different world where I was a gifted business person. These people come to a chemistry class, they're learning about molecules, and the question they're asking in their head is this: how can I monetize this information? How can I? Right? They're learning about the molecular structure of natural female hormones, and they recognize that female hormones fluctuate. They fluctuate during pregnancy, they fluctuate during puberty, they fluctuate during, what's the other stage again? Menopause, many stages in life. So if there is a natural chemical that's function is related to its structure, then you can make your own. And the one that you make in the lab, you can actually patent it. And if anybody uses your recipe, they have to pay you money. See, business people in chemistry classes, I study them. That's what I do. I don't do it. Okay. So when you make your own chemical, your chemical is called synthetic because it was made in the lab. Synthetic, the fake one. But that is used to supplement for the natural one if the natural one is low for whatever reason. So here, for these natural chemicals, we have the synthetic version. Look at that. Somebody looks at chemistry. They think, how can I monetize this? They go to the lab, learn chemistry. Now they made their own chemicals. It is slightly different. So they're telling you here the natural one is missing the carbon-carbon triple bond, but the fake one, we call it synthetic, has the carbon-carbon triple bond. Of course, we know that all these drugs do have side effects, right? Because your body recognizes authentic chemicals. It's like, this is not natural. And so you have all these side effects. But anyway, so the synthetic versions of these birth control pills do have the carbon-carbon triple bond. Anyway, so here's a comparison of the two. Oh, guys, hold on, hold on. Oh, hold on. Sorry, guys. My friends don't know I'm doing this on the side. I'm doing this right now. So hold on. Okay. Let me hold on a second. Let me let her know. I'll call her in a little bit, so she doesn't call me back. This is what happens when you got friends and trying to teach. Give me just a moment. Let me let her know I'm recording. Okay. So here we have the natural hormones, and these are the synthetic ones. Okay. Okay, so what I want to do here, I'm looking at the reactions of these alkenes, and I'm thinking, I'll work as far as I can, okay? Because this may not go that long. Okay, now that we know the background story of the alkenes, we're now looking at the reactions of alkenes. We saw that alkanes really only had one type of reaction, right? So real quick, in alkanes, we saw that alkanes underwent combustion. That means you can burn them. And with a combustion reaction, we just saw alkanes adding to oxygen to form carbon dioxide and water. Oh, hold on a second. Let me add the page in the right place. Okay, let me use a simple alkane. Here, add oxygen to get carbon dioxide and water. There. Okay, I'm actually going to balance it today because yesterday I had been talking for a while and I was tired. Okay, how do I balance this real quick? If you're asked to balance this, you itemize, right? We have one carbon, we have four hydrogens in this formula. I'm itemizing and writing the elements below the formula so I can be consistent, right? Here I have one oxygen. I'm sorry, two. I'm saying one and I'm writing two. I have two oxygens. I have one carbon. I have two oxygens, right? Once again, itemizing. And then I have two hydrogens and I have one oxygen here. Okay. So the goal of balancing is to make sure when you itemize, you have the same number of atoms on the left compared to the right. Okay. So you want to make sure the total oxygen on the left matches total oxygen on the right. Total carbon matches total carbon. Total hydrogen matches total hydrogen. Okay. That's the bottom line of balancing. So let me do a quick check. Carbon and carbon look balanced. Okay. As I'm doing this, I don't have a lot of time to discuss balancing. I'll say this real quick. Because I have one formula on the left that has an oxygen, but I have two different formulas on the right that have an oxygen, you want to deal with that complicated case last, okay? I will balance carbon first, and I'll balance hydrogen. So my carbons appear balanced. My hydrogens, oops, they're not balanced. We balance by multiplying the present number of atoms with whole numbers, okay, if possible. So I want to make the hydrogen on the right match the hydrogen on the left. So the hydrogen on the right has 2, the one on the left has 4. So I'm going to put here times 2 to make this equal to the one on the left, 4, okay? Now the hydrogen is balanced, but the hydrogen is in the same compound as this oxygen up here. So if I double the hydrogen, I also have to double the oxygen. So 1 times 2, because in the same compound, equal 2. Okay, so what have I just done right now? I had to double both the hydrogen and the oxygen. The hydrogen match the one on the left. The oxygen, because when I'm done doubling, I'll take the multiplier I have here and place it in front of the formula water. And then that 2 will apply to both hydrogen and oxygen, okay? Hydrogen is balanced. We're done. Carbon looks balanced. We're done. Now let's consolidate our oxygen. On my right, I have 2 plus 2 oxygen to make 4, right? On my left, I have 2 oxygen. How do I make my left oxygen have 4? I just double these 2 to get 4, and then now they match. Now this is equal to that. The multiply I wrote here goes up here, and this equation is balanced, okay? I only have time to do one, so, because, yeah, I need to go back to this topic here. So now we're looking at reactions that alkanes undergo. Alkane undergoes a lot of different kinds of reaction. The biggest one is called the addition reaction. Okay, the addition reaction happens around that carbon-carbon double bond. We don't see addition in alkanes because alkanes don't have a double bond for this type of reaction to happen. Remember, those bonds, those functional groups, have specialized reactions that go with the functional groups. So we're seeing addition reaction where, oh, it says wherein new groups X and Y are added to the alkene. One bond of a double bond is broken and 2 new single bonds are formed. So what they're saying here is, let me illustrate that. We start off with the carbon-carbon double bond. This is our alkene here. Oh, I added my hydrogens. This is our alkene here. Okay, so in order to add to X and Y, one of the 2 double bonds have to break. So I'm going to break the lower one. So the bond breaks apart between the 2 carbons, only one. And then it breaks apart so that each carbon now has kind of half a bond, which is like 1 electron. So it breaks apart to look like the, oops. So it's like carbon, full bond, full bond, full bond, full bond. Let me now write this vertical, sorry. These are the original bonds. And then the new bonds, I'm going to draw them really short right here because they broke apart. These are the new bonds, okay? So bond broken. Okay? Now, while the carbon is breaking one of its bonds, the same thing is happening with this X and Y. X and Y, they had a bond together. Let me try to draw this like that. Now they have short pieces. Also, bond broken. Okay? So again, bond broken for both of them. I guess I can write one big bond broken. Okay, so the X takes this little piece of bond and attaches right here. Same thing with the Y, attaches right here. So they take kind of like their short pieces of bond and attach them where carbon and each carbon broke a bond. So we end up with now carbon, carbon, these are the original bonds. Do I have room? Oh no, I wrote too big. Y'all can see though, right? Now we end up with X down here and then the Y down here. So these are added. They kind of just added, kind of like having 2 new employees. They were somehow together, broke this bond, and then they joined this. Okay? So that's what they're showing you right here. These 2 atoms, X and Y, join the carbon-carbon double bond. Or, well, now it's now a single bond. The X and Y joined the carbons. Okay? Okay. So this is actually being done as the alkene is hydrogenated. So hydrogenation is the addition of hydrogen to an alkene. Okay? And so we see this happening once again. Remember the double bond? This bond here breaks to bring in pieces here. This breaks, so you have 2 H's with tiny pieces. They use the tiny pieces to join the H. Let me use a different color here to illustrate this part. Does that say different color? Hold on. H, tiny piece. H, tiny piece. Bring it over here. Tiny piece. H, tiny piece. H, there. So it's something like that, right? And this is how we end. But in the end, that's how it looks, right? The two H's have added on, and then the double bond is not there anymore. Now we have a single bond. And this is called hydrogenation, the adding of hydrogen while you're breaking up a bond. So the catalyst here, palladium, is important to speed up the reaction. So you want to make sure when you're completing this reaction, you have to include the metal catalyst, palladium. Okay? So what we're saying here is you can convert an alkene into an alkane by hydrogenation. So they're saying here, bottom line, an alkene can be converted to alkane by adding hydrogen and palladium catalyst. Hydrogenation, right? So now we're learning how to go from one functional group to the other. Okay, that's the skill. People get paid loads of money. When I say loads, it's not that much. In the world of science, yeah. Science is not like business, right? People in business get paid way more money. But in the world of science, comparing one scientist to the other, people who do organic chemistry, they get paid decent money. How about that? Decent. So here we're seeing an alkene becoming an alkane, right? The double bond that was there disappears as the hydrogens come in. Now we have an alkane. Okay, now we get to draw our own products. Yay. Let's see right here. Let me pick. I'll work this one here. Then I'll work, ooh, this and this. Okay, so here, the hydrogen's coming in. The palladium is just helping out, right? So I have 1, 2, 3, 4, 5 carbons. Okay, so my product will be 1, 2, 3, 4, 5 carbons, right? But the hydrogen can only go to carbon 4 and 5 because that's the only place where there's a double bond that can be broken to accommodate them. Remember, the rest of these have the maximum amount of hydrogens present, so you can't add any more hydrogens. Okay, so I'm gonna draw it out so y'all can see. H H H H H H H 1, 2, 3 double bond H H H. Okay, the two new hydrogens, the newcomers, they can only go one place. They can only go down here. But for them to come down here, this bond has to break. Oops. So this is my answer. This is my final answer. The bond broke, the one bond broke, the other one still remains, and this is the product. Product. Right here. Okay? You just bring in the hydrogens where there's room. You can't just put them in the other places because they're saturated, right? They're full. It's like there's no room at the end. Saturation. Okay. I'm going to work on this one and then this last one here. So same thing. I like the red better. It's a lot brighter. Okay, I'm not going to expand this one here. I'm going to leave it as is. The only room for the hydrogen is here and here. So I'm going to leave this as is. CH3, C. I'll come back and erase this. Don't worry. CH2, CH, open parentheses, CH3, close parentheses. Then we got the H down here. Then we got the CH3 here. We know the hydrogens can only go to the carbons holding the double bond, right? So I'm going to erase one double bond. Oh, there. And then I'm going to bring in my hydrogen with a different color because when they show up right there. That's it. That's my product. So I go from here to here by adding hydrogen with the palladium catalyst, and that's my product. Now from here to the product, hydrogen first. Hydrogen is the one that's being added. Palladium is just a helper to make it go faster. Okay, so here I know you got to add each hydrogen, one to each side of the carbon holding the double bond, right? So one will go here, the other will go here. So in my product, let me draw my structure. I'll do this out here. Okay. I have CH3. I know my one hydrogen is coming here. The other one is coming here. So I go in here and I erase this. Oops. I meant to erase just the second bond. Okay, there. Now, remember that in the skeletal structure, we don't usually show the hydrogens that are in the middle, so they can actually draw this like that, or they can make it just like this as a product. Ta-da! Like that, CH3. This is a part because the H's are implied. Okay. Oh, now we're moving on to something called hydration. Let me hydrate. No, for real. Hold on. In the world outside of chemistry, hydration is done when you're thirsty, right? You drink water. Can you turn the air on, please? It's kind of warm. Thank you. The air conditioner is a little far from me, okay? A little. Okay, so hydration is when you're adding water to an alkene. Well, why do we want to add water to an alkene? I think an alkene is fine by itself. Well, look at what happens when we add water. When you take an alkene and you add water to it, this is a water molecule rewritten in a way that serves our ultimate purposes. Look at what we get. What? Yes, we can take an alkene and make an alcohol out of it just by adding water, but it needs a helper molecule, a catalyst. So the helper molecule here is sulfuric acid. So you can't just write water. If you add water to an alkene, nothing will happen. It does require a helper molecule, which is a sulfuric acid. Okay, and the acid acts like a catalyst to make the reaction go fast. These reactions are usually very slow. Okay, so just like we saw before, you want to rewrite your water molecule in a way that makes sense in the addition process. H2O is essentially H and OH, right? When you combine them, you get H2O. So you can see how this bond breaks, leaving the H with a tiny little bond and the OH with a tiny little bond here. And then, just like before, the carbons in the alkene break apart there, tiny little bond, tiny little bond. You have these original bonds here still present. And then the H comes here, and the OH comes here. Now, this does get more complicated, but we are still in the non-majors class, so we're trying to keep it simple. You see how the OH came here, and the H came here? This is still addition reaction. But since we are adding a different kind of chemical from before, it's called hydration. So real quick, we have looked at hydrogenation, adding hydrogen with a helper molecule, palladium or element palladium, and then hydration. Hold on, my spelling. Adding water, and this time our helper is a whole molecule, sulfuric acid. Okay, hydration, hydrogenation. Okay, let's go down and see. So yeah, by doing this, we're now able to make alcohol. So these big brewery places, if they want to make, they can make the alcohol like, not, this is mostly isopropyl alcohol, other kinds of alcohol. The one that people drink, I think, is made from a more natural method, right? This one here is when you're trying to synthesize alcohol, like rubbing alcohol. Remember last year when it ran out? Man, I kept trying to buy it in the store. I did have 2 bottles of alcohol. I always keep stuff just in case. But when it was running out last year, yeah, companies were doing a lot of this to make the rubbing alcohol. Okay, so here they're showing you once again. I'm going to write this down here. Okay, the incoming group can only go here. Wait, let me change the color. Can only go here and here, right? So we have our water. This is H2O written in such a way that it makes more sense. This bond breaks, so you have a free H, and an OH. I'm trying to keep it simple, right? So the H comes, yeah, in reality, the H is positive, the OH is negative, but we're not going into all those details in the mechanism. That's for the majors class. We're keeping it simple here. The H comes attached to one side, and then don't forget the double bond has to break. Let me see if I can do that. Oh, there. Whew, that's a very uh, delicate process. And the OH comes here. And then, of course, the bonds rearrange, and we have our product, the alcohol. So we go from alkene, and now we have made alcohol. Okay? Our product is an alcohol, and the double bond is gone. It got sacrificed to make the alcohol. Okay, so over here is asking you what product is formed when each alkene is treated with water. Okay, so what I'm going to do here is I'm going to be done in 10 minutes because my ears are really, yeah. So I'm going to stop at 10 minutes. I'll just finish the rest of this later. What product is formed when each alkene is treated with water in the presence of sulfuric acid? So to all of these, you're adding water. Oh, I have to write it in the proper way, H-OH, and then sulfuric acid. Okay, so I know my product is going to come over here. To one of these, I'm going to add H. To the other, I'm going to add OH, and then this bond is going to break. So I'm just going to copy it from there. CH3, CH, O. I can write it like this if I want to, because this is actually makes more sense. Single bond to just show where changes happen, right? You can write it so many different ways. Yeah, addition reaction. This one here, plus H, OH, H2SO4. Let's see. Oh, there's a rule with this one here. Because you see, you can put the H here, you can put the OH here, or you can switch them around. So there's a whole rule that goes with this one here. So I'm trying to keep it simple for you guys. So I'm going to show you two possible products, right? In one case here, it's called Markovnikov's rule, and it gets really complicated. I'm trying to keep it simple for this class, y'all. So I'm giving you these two answers, right? I'm going to give you two answers because they're two variations. H2SO4. So this is a rule that helps us figure out which of the two possible answers will be formed. Okay. In one case, the H adds to the top carbon, the OH adds to the bottom. So we get this structure right here. CH3, the H adds here, so it disappears. Then the OH adds here. So they usually leave this H out. It's implied that it's there. Oops, just the H. In another case, these flip. The OH adds next to the H, then the H adds, the OH adds next to the CH3, then the H adds on the other side. So these can add either places. So sometimes they will show you both products like this. So you have CH3 and then OH, like that. Because the H is right here, but remember the H is implied, so they won't even show you that. There. Okay. I won't work on this one here because I think this one is straightforward. I think I skipped over Markovnikov's rule because it's more complex. Yeah, I did. There's a rule that explains that part, but I skipped over it because it gets more complex. Okay, let's go back to the food. Okay, I'm sorry. I'm excited. Because in other chemistry, we don't get to apply stuff to real life. Okay. So we're told here butter is made up of saturated fatty acid chains and is a solid at room temperature. That's why it tastes so good. Margarine, it's okay. It's synthetic product that mimics the taste and the texture of butter. How do we make margarine? Margarine is prepared from vegetable oils derived from unsaturated fatty acids. Okay, so butter is saturated, right? Long chains of alkanes. No double bonds. That's why it's packed so tightly and it's a solid. Margarine, though, is synthetic. It's made up. Margarine didn't start off as a solid, it got made into a solid. So how do they make a solid? They start off with vegetable oil. Oh, they start off with long chains that had double bond. So if the long chain with double bonds are liquid, how do they make the vegetable oil a solid? Guess what? They partially hydrogenate them. They pass hydrogen through the oil, and what this does, it breaks the double bond, that's liquid, and makes single bonds. And this is a solid. Many of these, right? Remember, there are many double bonds, many double bonds. So it breaks double bond. These are broken as the hydrogens attach to make it a single bond. So it goes from being a liquid to a solid. So if you stop by Walmart, okay, and you look at the tub of Crisco, it says on there hydrogenated fat or hydrogenated oil. Look at it. And so they don't break all of them, they break some of them, right? Because they partially break some of them, margarine is still healthier than butter. When they said they can't believe it's not butter, I don't know. But the point is that the process allows only a few of the carbon-carbon double bond to remain on the chain. So the few that remain make it healthy, right? It is solid, but it's not naturally occurring. So it's a fake solid. It wasn't naturally solid. It was made solid. That's how they have avocado butter. You're like, wait a minute, what? Or olive oil butter, they just take the oil and then they pass hydrogen through it with palladium and then make the stuff. Now, in no way am I recommending you go home and start your own business on Etsy and make the stuff, right? Not at all. So here they're showing you oils. These oils, so this is a lot better, right? This is better for your health. Because you see, they have the double bond, cis fat's good for you, cis. And then when they hydrogenate it, then you have the stuff that is now not butter, but it looks like butter. But it's when it has a bunch of double bonds, you can see here, it's a lower melting point, it's a liquid at room temperature. Once they remove some of the double bonds, now it has a higher melting point, it has fewer double bonds, and it's a semi-solid, not very hard like butter, but a little bit harder. Okay, once again, business people, sit in the chemistry class asking the question, how can I monetize this knowledge? Think like that, okay? Don't be like me. Think like that. So we are back here. So here's where they're making that point, right? Why is trans fat bad? Margarine or butter? Okay. Y'all know the correct answer, right? The politically correct answer is margarine, but come on, occasionally. Butter, I have some butter. On special occasions, that's when I eat me some butter. On a daily basis, no. I do the right thing and I eat margarine. I mean, you can't eat margarine all the time, right? So occasionally I'm like, no, this feels like a butter day. Yeah. So this is showing you why trans fat is bad for you. Trans fat and saturated fat has the same characteristics. Their molecules are neatly acyclic and they're neatly linear. You see the shape? Straight. So these are the ones that pack very tightly and they form that solid. So trans fats are usually solid. They have what's it called? High melting point, high boiling point. They're solid at room temperature. These are the ones that form plaque, but they taste so good because they're like bacon and butter and all those things that are tasty. Okay, so we're moving on to polymers. I mentioned polyethylene, right? Polyethylene, these are the many, poly means many, okay? So we're dealing with polymers here. Polyethylene, I mentioned before, are many ethylene molecules tied together to ultimately make, you know, the tub that we have water in, the water jug or the milk jug, to make those. The other one is the fabric polyester. Those are not allowed in the lab, right? Just because they're chemicals that can easily burn. I mean, you can wear polyester from whatever, anytime. Just when you get to a lab, it's dangerous to have polyester around fire. Okay? Okay, so polymers. Polymers are large molecules. So poly means many. Mers is the chemicals, right? These are large molecules made up of repeating units of smaller molecules. The smaller molecules are called monomers, okay, the individual units of the molecules. So poly is many of those repeating individual units. And you see a pattern over and over again. Hopefully y'all know about PVC, the PVC pipes. PVC pipes are made from the repeating units of this. So we have this right here, this right here, this right here. PVC, they showed you a small part of it, kind of like DNA, only not as interesting. We have polymers, okay? And then here we have polyisobutylene. This one here, styrofoam. This is styrofoam. You got that, right? 3 units of each. You got this, you got that. Repeating units, right? So they're showing you 3 of each. Okay, so you have natural polymers and then you have synthetic polymers, right? Think about this from the point of view of business. How can we monetize this? So things that are synthetic are made in lab, okay? This is like a stuff that you can patent, the stuff that you can sell to others, the stuff that you can make money from. In polymerization, the weak bond that joins the 2 carbons of the double bond is broken. One of the bonds get broken, and then a new strong carbon-carbon bond, the single bond, joins the monomers together. So what they're saying here is the double bonds are not as strong as the single bond. Can you imagine? Together they're strong, but individually you have 2, well, one bond, the first bond is stronger, the second bond is weaker. So all they're saying is the second bond gets broken, okay? So this is addition reaction like we just saw. So why are they calling it polymerization? Oh, when I was learning this stuff, I'm like, why are we using a different name to describe the same thing? Different group of people, different purposes. The first one was just straight up chemistry. This is applying it to industry, right? You're trying to make a polymer. So we are making a polymer, polymerization, making a polymer. The name here ties to the goal, right? Like hydration, adding water, hydrogenation, adding hydrogen. Now polymerization, not adding a polymer, no, making a polymer. Okay, so here they're showing us how they're making a polymer using 3 monomers. So we have ethylene monomers. We have 1, 2, 3. So they're showing you here the bond is going to break. The double bond will break and it will reform. So I'm going to show you here how it breaks. It's a, yeah. The top bond, doesn't matter. It can be the top or the bottom. This bond breaks between these 2 carbon. Let me call this carbon 1 and 2. And then here 3 and 4. And then 5 and 6 for this to make more sense. So the bond, the second bond between carbon 1 and 2 breaks. Okay, when it breaks, the electrons used for that bond are now repurposed. And the bond, the electrons are taken by carbon 2, and carbon 2 forms a bond with carbon 3. So these are taken away from here. So even though it shows this is God, and it forms a bond with carbon 3. So let me draw it here on a different page because I feel like I have more freedom when I draw it out myself. So here, CH2, oops, CH2, CH2, okay, and then CH2, 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 okay. So carbon 1, 2, 3, 4, 5, 6. These are about to form a polymer. You're joining individual units to form a polymer. So I can erase one of the bonds here. Oops, gone. And then use that bond. Actually, you know what? Let me use different colors so maybe that can make more sense. I'm trying to make this up as I go. Okay, so all the blue bonds get broken. Okay, because it's just one of the 2. It doesn't really matter which one. So once the blue bond gets broken, show that here. Let me get this just right. Okay, got it. Then carbon 2 uses the electrons from the bond to form a bond with carbon 3. Like, seriously? Yes, it does. Same thing happens here. And the one that gets the electrons, oh, no, 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 no. I went the wrong way. The one that gets the electrons, hold on. Okay, is the one on the right. Okay, so carbon 4 takes the electrons and forms a bond with carbon 5. Here, carbon 6 gets the electrons when the bond breaks. Hold on. Okay, there. And carbon 6 will form the bond with whatever is coming in next. In the end, you get this long chain. And it keeps going on until you have a long chain of chemicals. Okay. Yeah, they're showing you examples, right? Let me show you PVC and propane, polypropylene. Oh, duh. I'm sorry. I won't show you any of these because I have some down here. I'm sorry. Yeah, they're showing you here. PVC is also used as blood bags and tubing, right? For dialysis, for what's it called? IVs in the I want to say the lab in the hospital. Or you have polypropylene that's used for plastic. No, this is not used for plastic. That's polyethylene. Polypropylene is used for syringes. And then you have Teflon that's used as dental floss and different things at home. Anyway, I forgot I had questions here. That's okay. I'll go ahead and work this out. Oh, yeah. I recognize the video is long, right? I don't know how long I have before this is over. Feel free to pause, write down the time that you pause it and walk away and come back. You don't have to sit and watch this in one sitting. There's no requirement. Just pause, come back, write the time where you stopped, and then come back and then take breaks. Because like even as a teacher, I'm struggling a little bit, but I'm standing up, so I'm good. Okay, I'm gonna do this one here and this. Okay, I'm gonna draw what polymer is formed when each compound is polymerized. Okay, so I'm not gonna really say what is formed. I'm just gonna draw it. I'm gonna draw. It's actually called. There's a monomer, dimer, and trimer. I'm gonna draw a trimer of each of these. So when they're asking you what here, just draw trimer. I just realized they weren't very specific on this question here. Okay, so I'm gonna draw a unit where we have 3 of these. Let me start with the second one here. So I have C, this is H, H, C, CH3, CN. Okay, so you see how I'm drawing it like this? This is just the first and the second, right? Next to that, oh, let me just cheat. Not really, but let me copy and paste and see if I can do this. Will it work? Oh, yeah, there. So I can move a little faster. And there. So y'all saw that, right? Okay, once I have this, I know one of these bonds is going to be broken. So let me see. Can I break the bond? Yep. 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 Okay, so the bond that got broken, I'm going to use a different color to show the new bond that's formed. Form this bond here. Form this bond here. There. There. And I just drew the trimer. Trimer as in I connected 3 different monomers to make this little piece. Okay? So all I'm doing here is even though the bonds are angled, I'm making them vertical so I can bring in the others. Okay, so I'm going to work on this one here. I use a different color. So I'm going to draw these in the middle. So C, the H is up, and then this whole benzene ring. Right here. This is down like this. This has 2 H's, up, down. Okay? So this is 1 unit. Let me copy and paste, y'all. Gotta be efficient. Copy, paste. Oh, oops, no. Paste. Okay, better. Paste again. Oh, okay. Okay, so I'm gonna go in here and erase that. Can I bring that here and erase that? Bring that here and erase that. Okay. So I'm gonna form three new bonds because three bonds got broken. I should bring in three new bonds, right? I use a different color for the bonds, different color, y'all. Here, here, here. Of course, if there's something else going on here, this continues, right? So you get the trend, right? That's how the polymers are built. Do you see how I did it? I just converted these bonds and made them more vertical like that so that you can fit in the rest of them. So here, and that applies for this too. Oh, I just realized something. What if you're working backwards? What if you're working backwards? So if I have to work backwards, I just reverse this, right? You want to find the part that repeats. So I'm going to use the highlighter. This and this repeats. Of course, it's easier for me to say because I can see it, right? This repeats, this repeats. So bring the double bond back between these two. So essentially erase this, double bond here, erase this, double bond here, erase this, double bond here. Okay. Let me see. Yeah, so let me see. I'll do one for, that's what I was doing with this one here, right? You want to find the pattern that repeats. So I'll do it for this one here. The pattern that repeats looks like the CH, then this, then there's this, and then there's this. So this is going to be CH2, the monomer for that, double bond, CH, CN. That's the monomer. And we have these units 3 times. Okay? So hopefully you see that. Okay, let me scroll. I'm trying to see if I can get to the end today. I'll feel a lot better because I don't want to have to record this tomorrow. And at least you guys can then study and prepare for the exam. Okay, so we're finally looking at aromatic compounds, and these are studied with alkenes. Aromatic compounds, we're told aromatic compounds are composed, okay, sorry, I'm already getting fatigued. Aromatic compounds are compounds that contain benzene ring. Okay, so we saw the benzene ring before. This is the Lewis structure of the benzene ring, showing you there's 6 carbons with alternating double bonds, right? Double bond, single, all the way around. And then, of course, the carbons have the right number of hydrogens. This is the molecular formula. To make this compound, you need 6 carbons, 6 hydrogens. You have the Lewis structure here. You have the skeletal structure here. Skeletal. So they can ask you, what is the bond angle, right? Pick any one of the carbons and then count the number of groups. There is one group here, second group here, third group here. I've not forgotten. Then you pull this up here. Yeah, this one like we did before. 3 groups, we have 2 to pick from. Do we have lone pairs on this group? No, they're all bonded groups. So 3 groups where all 3 are bonded groups. Everything else we need is on this side right here, right? So 3 groups, bonded groups, bond angle 120. If they say shape, trigonoplanar, right? Or planar. This would be nonpolar, but let's see over here. So yeah, see bond angle 120. Shape, they didn't even say trigonal, just planar. Planar is fine too. Okay, so you see once again the role that this little sheet of paper helps over here. Let's set it on this side. Okay, so what did I say? I've mentioned this before. Each of these benzene, either this structure or that structure represents the same arrangement of atoms, but different location of electrons. These are pretty much the same as. You can use that structure there or that structure. Either one works. As it says right here, each representation is equivalent. Okay, the physical properties of the aromatic compound hydrocarbons are, oh, sorry, the physical properties of aromatic hydrocarbons are similar to the other hydrocarbons. They have low melting point. The intermolecular force is London dispersion force only because they're hydrocarbons. Okay, and the boiling point is low. The melting point is also low, and they're not soluble in water. Why? It's got 6 carbons and 6 hydrogen only. They don't have oxygen or chlorine, nothing else. It's carbon and hydrogen. So these are hydrocarbons. Don't like water. They like oil. Okay, so tamoxifen is a medication drug used for breast cancers that require estrogen for growth. Tamoxifen, you can see right here, it has these 3 benzene groups. It has those benzene groups right there. It also has a double bond. So this is called alkene, right? It also has, man, it's got a lot of functional. Do you see how these medications have a lot of functional groups? There's a carbon here, an oxygen, and a carbon. This is an ether. There's a nitrogen here next to a carbon, but I don't see an oxygen nearby. So that will be an amine. Remember from yesterday? Okay. So we need to know how to name benzenes. Okay. With benzene, it says here, name a benzene ring with one substituent. So we're doing that first. You want to name the benzene ring that has one substituent. That's our goal. First, you want to name the substituent. We always start from the longest chain. So our longest chain here is benzene. So we're going to start from that. Our longest chain, this is the longest chain. So our longest chain here is going to be benzene. And then whatever is not benzene is a side group. 2 carbons, ethyl. So this is going to be ethyl benzene, like it says. Longest chain here again is benzene. So just like before, name the benzene longest chain first. Side group, 4 carbons, butyl. You're probably wondering, why am I not writing numbers? Because we only have one side group. If we have 2, we have to provide numbers. Okay? And then here, side group. In the world of organic, which is where we are, chlorine is not called chloride, not as a side group. It's called chloro. Yeah. Different group of chemistry, different nomenclature. So this is called chlorobenzene because you have one chlorine attached to the benzene. So benzene is the longest chain. Side group, chloro. Different group of chemists, different people. So here we're being told that some of these monosubstituted benzenes have common names that you have to learn because scientists use these names. This is where I'm like, what's your number? Can I call you and complain? Why can't we stick with the one name you gave us before? But think about it. You have different names. People call you different names. Some people call you whatever your name is. Some people call you sweetie. Some people call you, I don't know. Anyway, so different scientists have different names for the same chemical. Now, they have to be accepted names. There's a technical term, the IUPAC name, and then there's a common name. So this is the IUPAC name, the one that's technical, right? And then there's a agreed upon casual name, like methylbenzene, methyl group benzene. That's called toluene. Why? I don't know. That's the group they chose. That's the name they chose, toluene. Okay, so you will see toluene in the place of methylbenzene. You just have to learn it. You can be upset. I was upset. I got over it. And then hydroxybenzene. I'm going to leave it at that. Hydroxybenzene, right? Phenol. Really? Yes. Phenol. That's the common name. Okay, hydroxybenzene. We heard of hydroxy at some point last year, right? We'll just leave it at that and move on. Okay, and then we have benzene with this amine group. NH2 is called amino, right? Like amino, no, amino. So the technical term is aminobenzene, but we don't usually use it on an everyday when you're reading books and stuff. They just call it aniline. Okay, so aniline is this group right here. So together, these are called aniline. Okay, now we're gearing up for naming benzene groups that have more than one side group. Okay. First of all, as you're looking at this, you want to ask yourself as you're looking at it, are you seeing any one of these scenarios here? So I'll keep coming back to these, right? We have toluene. Hold on a second. Let me grab my book for a second here. I am getting a little fatigued because I was going to stop in 10 minutes, but I was like, you know what? If I can push this through and just get it done, I'd rather get it done. My friends can wait. I'll call them back. Okay, real quick. So because I'm getting a little fatigued, I want to write this down so that I'm doing good. Because this is not math. Okay. So this is toluene, phenol, and aniline. I think I'll remember it. I just haven't taught this class in 3 years, so I want to make sure that my brain doesn't just, especially when I'm tired. Okay, so close, so close. So we're now dealing with the di-substituted benzene. Di means two. So now we have two side groups. Benzene with two side groups. So the purpose here is to give you the technical term down here of the side group and then the more familiar term, okay? This benzene ring has got two side groups. You can see the benzene ring is called benzene. This side group is called ethyl. This side group is called ethyl. Okay, so since you have two side groups, benzene, yeah, you will number one of them carbon 1. Doesn't really matter here. 1, 2. So the ethyls will be consolidated because they're the same side group, and it'll be 1, 2 dash diethyl benzene. So 1, dash diethyl benzene. 1, 2 dash, sorry, 1, 2 dash diethyl benzene. This is the IUPAC systematic name. Okay, let me move to this one here. Once again, same side name or same side chain. So this is going to be 1, 2, 3, right? So 1, 3 dash diethyl benzene. And we have that here. This is the IUPAC name. And these are opposite to each other. 1, 2, 3, 4. So we have 1, dash 1, 4 dash diethyl benzene. Right? So right here on carbon position 1 and 4, we have two ethyls. Longest chain is benzene. This is once again the IUPAC. Okay. Well, there are common names to refer to these positions. You have ortho, and the ortho name just says you can use O in the place of 1 and 2. So 1 and 2 is ortho. Okay, you see that? 1 and 3 is meta. And then 1 and 4 is para. So para is when you have one group in position 1 and then the second group way across. And then meta is when you have one group in position 1, the second group kind of like, 2 carbons away. And then the ones where you have the side groups close to each other is called ortho. Okay? So give me just a moment. I'm a little rusty on this. So I just want to kind of make sure I give myself some accountability here so I don't get lost. I mean, I probably won't. I'm more concerned because I'm tired, right? But I'm close to the end. Okay. So when it comes to naming groups where the groups are not alike, just like before, remember what they like. Alphabetize them. If you have to put the numbers from small to big, right? Alphabetize them. If there are two groups in the benzene ring that have different names, alphabetize the two substituent names. So here, remember, chlorine is chloro, bromine is bromo. Okay? So here, you can give numbers, but they're not even using the numbers anymore. So we'll go straight for the letter. Okay? Now remember, ortho goes with 1, 2. So you could say 1, 2. But we're not even using the numbers. So what this is going to be is O, which takes the place of 1, 2. O, bromo, write the bromo first, chloro, benzene. This looks like a poem. Oh, chlorobromobenzene. I don't know, guys. This is it's yeah. It's getting to that time, right? And then here, position 1 and 3, that is meta, right? Yeah, it's meta. So this is fluoro, and this is ethyl. If you're using the numbers, you use 1 and 3, but we're not using the numbers. But I like to use them because it helps me remember what M is. So here we're going to have M in the place of the numbers, dash, ethyl, E first before F, fluoro, benzene. Okay? Okay. So we get a chance to name these di-substituted benzene where we have one of those common benzenes, right? The common monosubstituted benzene. So we're told here for our di-substituted benzene, if one of the two substituents is part of a common root, then name that part of a molecule as a derivative of that monosubstituted benzene. If you can identify one of those common benzenes, section that out as though it was your longest chain. That's what they did here, right? The benzene group and the methyl together make toluene. Remember we said before methyl benzene is toluene. So instead of writing methyl benzene, because you would normally write, what is it? P dash bromo methyl benzene, correct? But remember, methyl benzene together makes toluene. So you write P dash bromo toluene, if I can spell correctly. And then here, if we're using the official term, you write, because these are next to each other, O chloro, this is chloro, right? Chloro. I forgot to label these. This is methyl, this is bromo, this is chloro, this is hydroxy. O chloro hydroxy benzene, if I can spell this right. But hydroxy benzene has a common name that's called phenol. So it's O chlorophenol. Imagine, yeah, that. O chlorophenol. Okay. So when we're naming many side groups on a benzene, polysubstituted benzene, number to give the lowest position numbers around the ring, alphabetize the substituent names. When the substituents are part of a common root, use that instead. Name the molecule as a derivative of that monosubstituted benzene, and then put the common root substituent as carbon 1. Ooh, but omit 1 from the name. Okay. So what they're saying here is we now have a polysubstituted benzene. We have a benzene that has many side groups, right? More than 2. It's not di, it's not mono, it's tri. But just the generic term here is polysubstituted. So you have to figure out which one to number. As you're looking at this, I'll actually go ahead and give them names: ethyl, propyl, chloro. So let's look at different variations of numbering this. They said back here, number to make sure that the substituents end up with the lowest number possible. So let's look at different combinations before we land at what they have, right? I'll look over here and see. What if I personally wanted chlorine to be 1? If chlorine is 1, and this is 2, this is 3, this is 4, my numbers end up being 1, 3, and 4. Okay? What if I wanted this group to be 1? 1, 2, 3, 4, 5. My numbers end up being 1. So the numbers I'm reading out are the numbers that go with the side groups, right? Okay, my numbers end up being 1, 2, 5. Okay. Now let's go with the one that they chose, because apparently they are right. They chose this one being 1, this being 2, this being 4. 1, 2, 4. So the one they selected is apparently the best. Let's see why it's the best, right? This here is apparently the best. Okay, they're all the same with the one is fine, it's the same. They want these numbers to be the smallest possible. Between this 3, 2, 2, 3 is the highest, so that's not good. 4, 5, 4, 5 is higher, so that's not good. So these combinations I picked for numbers are not good because they have the highest numbers possible. I know it's weird, but remember, I'm trying to meet this goal. You want to number in such a way that I give the lowest possible numbers around the ring. So I checked to make sure. I actually wrote it down, okay? So based on that, this is what they have. Now that we have this, we know we have one ethyl. It's on carbon 1. This is 2 propyl. This is 4 chloro. When we're writing it down, we have to alphabetize. C comes before E before P. So 4 chloro dash 1 ethyl dash 2 propyl benzene. I know. What about this one here? This case here, you can't just pick and choose where you want to number. They said it right here that if you have one of those common substituent molecules, the ones that have either, if you have toluene, phenol, or aniline, the benzene ring that had those special side groups, then you have to put a 1 to that common substituent. That has to be your carbon 1, but don't use 1 in the name. So what I mean by that is over here, okay? Because this amino group plus the benzene make up aniline, this position has to be carbon 1. Then you want to go counterclockwise so that chlorine has a small number. Not because we're trying to give chlorine a small number, we're trying to give all of them small numbers. So let me try clockwise first, okay? I know this one has to be 1. That's what the rules say. What if I go here? 2, 3, 4, 5, 6. I end up with 1 for nitrogen. So I end up with 1 for nitrogen, 3 for chlorine, and then 6 for the other chlorine. Okay, let me compare with the one they picked because I think there's only 2 combinations here. The one they picked was what? 1, 2, 3, 4, 5, 6. This is what? Counterclockwise, right? We end up with 1 for nitrogen, 2 for the left chlorine, and then 5 for the right chlorine. You see how these numbers are larger, so this is smaller, so this is the one that wins that orientation. Okay, so it's going to be 1, check, 2, 5. This whole structure here, the longest chain, is now called aniline. So we just now have to name the side groups. The side groups are on carbon 2 and carbon 5. So this is going to be 5 chloro and then 2 chloro. But the side groups are the same, so we can combine them to make 2, 5 dash dichloro. Let's see what they do. Oh yeah, 2, 5 dash dichloroaniline. Okay, I mean it seems like a lot, but remember I'm following the same pattern. Okay, as we move along here, we're seeing common sunscreens that use benzene. They have benzene in there. PABA, PABA. This is a p-aminobenzoic acid, a chemical used in sunscreen. And then we have vanillin, vanilla flavor, that uses this chemical right here. Okay, you can see the benzene ring and then the side groups. Okay. Oh, we're close to the end. I'm happy. Okay, so right here, name each of the following aromatic compounds. With this here, let's see. Do I have a special group? No. Okay, so Oh, I'm going to use the letter O versus the numbering, okay? So these are how they relate. They're 1, 3, right? 1, 2, 3. So I'm going to use M. M dash. This is propyl. Oh, I can't spell. Propyl. This is ethyl, right? 2 carbons ethyl, 3 carbons propyl. And since they have a 1 to 3 relationship, I'll use M. If it's 1 and 3, I use the letter M. So M, ethyl, propyl, benzene. I didn't go in the right order, right? You can do the benzene first, and then you can name the side groups last. Okay? And so all we need is this. This is the answer right here. I'll go in the proper order this time. Okay, with this one here, do I have a special side group? Yes, I do. My special side group I see is this one right here. Okay? So that makes this carbon, carbon 1. This has to be carbon 1. Then this becomes 2, this becomes 3, this becomes 4, 5, 6. So my special side group and the benzene ring, this is methylbenzene. So it ends up being toluene. That side group is called toluene. Okay? Methylbenzene. And then let's see, what do we have here? I have 3 chloro, 4 bromo. So when I consolidate, I end up with 4 dash bromo dash 3 dash chloro toluene. Okay. Yeah. B comes before, ooh, my bad. B comes before C. Oh, now we're just naming. Oh, this is the end. Yay. Sorry for being too excited. Okay, so I guess I'll go through, since I've done this one here, this is similar to that, so I'm not going to do that one. I'm not going to do this one here. I'll do the other one. The longest group here is benzene. The side group here has 3 carbons, so propyl. So propyl, benzene, right? I can scoot this closer. No need for the number because you only have one side group. Let's see, the longest group here is benzene again. I have 2 side groups. This is called iodo. This is called ethyl. Their relationship, the positions is 1, 2, 3, 4. Because it's 1 and 4. 1 and 4, they use the letter P, right? So it's going to be P dash, which letter comes first? A, B, C, D, E, F? Okay, E. Ethyl. P dash ethyl iodo. That's a weird one. P-ethyl to talk about this one here, and then iodo benzene. Oh, okay. This one here has it's a special one, right? Hydroxide with the benzene has a special name, and that is phenol. Is this position 1? This is 2. This is 3. So the longest chain here is called phenol because it's one of those 3 that I mentioned. This side group 1, 2, 3, 4 is butyl and is on carbon 3, 3-butyl. There. So 3-butyl phenol. Let me bring this closer. There. Okay. So we're moving on and we see draw the structure. Let me see. Okay, I'm going to pick this, and this. Pentylbenzene, that's straightforward, right? So I'm going to draw this one here. Oh no. Oh no, copy first. Copy. 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 Okay. So here we are, starting with this benzene ring. Benzene. This is done. Chloro, but there's two of them, right? And they are O to each other. So remember, O stands for, I'm glad I wrote this, 1 and 2, because as I'm fatigued, my brain is like checking out. Okay, so O is position 1 and 2. So position 1 and 2, I have these side groups. Chloro, chloro, right? They're O to each other. They're ortho to each other. I have this written down here. Ortho means position 1 and 2. That's the relative positions. That's that. Next one is M, bromoaniline. So aniline is essentially the benzene ring with the NH2. Okay? Now this is understood to be position 1. So there's another group, bromo, and if it's M, it's 1 and 3. M is the meta that stands for 1 and 3. So this is carbon 1, 2, 3. On position 3, we have the bromine group. Okay? Then finally, we have benzene diethyl. Let me start from the right. Benzene, I'll draw the group right here. Benzene, this is done. 1, 2, diethyl. I'll call this 1, 2, 3, 4, 5, 6. Position 1 and 2, I have two ethyls. Ethyls have two carbons. CH2, CH3, two carbons. Let me do better. CH2, CH3, CH2, CH3. Okay, so this part is done, this two. And then carbon 4, I have a chlorine. Carbon 4, I have a chlorine. And I made it. Woo! 2 hours. I can't even count the time right now. It's a long time. Anyway, this is the end of chapter 11. I'll see you guys in the next chapter.